Well, welcome one and all. It's a pleasure, really a pleasure to introduce Tiffany Shaw to you. Tiffany is an assistant professor in our department. She has been with us a couple of years now, and before coming to Columbia, she was at NYU for 1 year as a postdoc, and prior to that, she was in Toronto working with Ted Shepard. She's done a lot of work on the stratosphere, and we'll hear some of it today, strat-trop coupling, but she also does many other things. And I hope in future visits, I hope this is only the first of many visits in coming years, you will talk about a broad range of things. Anyway, welcome.
That's right. Maybe I shouldn't hold this up. All right. Thanks so much, Lorenzo, for the introduction, and thank you all for coming. It's really great to be here. And I really wish I could stay longer, but unfortunately I'm only here for today. So what I'm going to do is tell you about some really interesting and what I think is very exciting new stuff that I've been doing in collaboration with Judith, who's here in the audience, along with a summer student who's helped a lot with the CMIP5 model processing. It would help if we dim the front. I'm not sure if that's possible. Okay, so I'm going to start just to give a brief introduction on the problem of interest. And so this is stratosphere-troposphere coupling. And for those of you who aren't familiar with the problem, I'll define some terms and really highlight for you the really key dynamical features that I'm going to showcase throughout the talk. And the interest will be in this connection to the troposphere, something that's been noted almost a decade ago, or just over a decade, that we're still trying to better understand and explain and sort of extract, for issues of seasonal predictability, and also for questions of the future. So how does this really work? And so what I'll really highlight for you in the talk is our contribution to this problem, and it's going to revolve around sort of coming back to the fundamental role of quasi-stationary planetary scale waves. So these are the waves that are forced by land-sea contrast. They have very deep vertical wavelengths, and this is what will be key for the coupling that I'll talk about. And the interesting thing will be to explore these from the perspective of extreme events. So these waves can undergo very extreme behavior. And what we'll find is that when this occurs, there is this very distinct coupling to the troposphere. And it has a signature in the stratosphere, including a strong impact on the residual circulation, which is the mass overturning of the stratosphere. And it has interesting implications in the troposphere from the perspective of the Atlantic. So there's this very distinct interaction. And then I'll go through, here we'll be mostly focused on the reanalysis, and then I'll springboard off of that to show you how the results here can help us understand how the models are representing this process and how we can say something about how good their troposphere is based on a metric that we use in the stratosphere, including their planetary wave structure and the Atlantic jet structure. So the basic ingredients of the problem are waves and mean flows. And so I like to show a schematic from Alan Plum from a review paper. And so here you're looking at from the summer pole to the winter pole in latitude, so zonal mean cross-section from the surface, let's say to the stratopause here in the dashed line. And so the main features of interest are the green lines here. They're representing as a schematic, as wave forcing coming out of the troposphere, which involves synoptic scale waves here. This is due to baroclinic instability, has very distinct wavelengths. In addition, we have planetary scale waves, okay? And these waves are interacting with both the subtropical jet in wintertime, this is the winter hemisphere, and the stratospheric polar night jet, which of course is receiving no direct sunlight, and we build up a very strong eastward moving polar vortex. And so what was shown early on in a very nice paper by Charney and Drazen is that when you have this very strong eastward flow, one can envision waves basically as they're propagating on this inhomogeneous medium related to the vortex, their vertical wavelength, okay, so their zonal wavelength is determined by the land-sea contrast, but their vertical wavelength is determined by this vortex, by this inhomogeneous medium. And what they showed is that in this particular case of northern hemisphere winter, the vertical wavelength of these waves is very, very deep, such that they are able to, let's say, propagate or exist all the way from the surface into the mid and upper stratosphere. Now, of course, when they reach such high altitudes, because of their amplitude's dependence on the inversive density, they actually become unstable and break, and that's what's represented by this shaded region. There's a convergence of what we call wave activity, or pseudomomentum. The energy from these waves is transferred to this polar vortex. In fact, it's a westward torque, which tends to decelerate the flow, and it's deflected then poleward through a bounce with the Coriolis effect. And that gives us the mass overturning of the streamlines here from the tropics with upward motion in the tropics and descending motion in the polar region. So this is the one pictorial representation of the Burr-Dobson circulation. And so the fundamental rule is the driving of this circulation by these planetary scale waves. Another thing I want to highlight is that, the circulation, of course, has implications for constituents, including chemistry. And that won't be the highlight of my talk, but I will highlight important interactions that can occur in this problem. The thing I wanted to point out is the timescales here span a very wide range of frequencies, okay? So the wave timescales, which are associated with vertical group velocities, these waves can propagate approximately 5 kilometers every day. So that's a pretty fast timescale, wave group velocity. Now the mass, the overturning stream function here is the Burr-Dobson circulation. It's on the order of years. And that, of course, is much longer. We also have radiative timescales, which span, days to months. And so there's a wide range of timescales that, I really want to highlight here because we're going to exploit some of the shorter timescales associated with the waves themselves. So this is the setup, and this is the climatology. And what can happen then is you get strong modulations of this climatology. And one of those modulations can be of the polar vortex. And it was shown in a very seminal paper by Baldwin and Dunkerton that if you just consider the polar vortex itself and its extreme behavior, for example, when it exhibits very weak events, very far below the standard deviation, or very many standard deviations below the mean, and you put them all together. So here, what they're showing is the so-called northern annular mode. You can think of this as the polar cap average geopotential height. So they put all of these events together, and this is the life cycle. We have pressure and time, so they synchronize the events here at 0 lag based on an index at 10 hectopascal. And what they find is that when there is this very weak vortex behavior, which is the index is based on that, the interesting thing from this paper is they saw these very persistent behaviors in the troposphere. And the behavior in the troposphere is not a modulation of the strength, but rather a modulation of the latitudinal position of the jet. So a weak vortex is coupled to an equatorward jet shift. And this persistence from 0 to 60 days is, of course, very interesting. And if one could exploit this for purposes of seasonal forecasting, it would be very, very helpful. Now, if you go to the other side of the distribution, for the strong vortex events, you see very similar behavior, but of course of the opposite sign. So a strong vortex event is coupled to a poleward jet shift. And just note the differences in the extreme values here, but there's certainly the same type of behavior. So we've got weak vortex events, which are very much related to stratospheric sudden warmings, which some of you may have heard of, where the temperature increases by the order of 50 Kelvin on a very short time scale, and the wind reverses from eastward to westward. And then strong polar vortex, which is associated with cold conditions and typically also ozone loss. So why is that interesting? Well, of course, as I highlighted already from the seasonal prediction point of view, but what we find also is that this is a very much this interaction occurs interannually. And so how would you get at that? Well, there's been a number of papers that have taken the approach of running experiments where they first use a seasonal forecast model, and I should say this is Duville at 2009, so let's just focus on the left. What's been done here is they've taken the French seasonal forecast model, and they've run it from 1971 to 2000. And the metric they're plotting as a function of year here, in red for the model, is the leading EOF, so the empirical orthogonal function of the 500 hectopascal geopotential height over the North Atlantic. And so you can see it varies year to year, and this is related to the North Atlantic oscillation. Now so the red is the model and the ensemble is shaded, and compared to the black, which is the ERA 40, the model doesn't have very much skill. The correlation is very small. So what was subsequently done in the right panel is the model was nudged, and by that I mean it's relaxed to the reanalysis data in the stratosphere, so above about 100 hectopascal and north of 20 north, okay, 25 north. And what you find for the same metric, which is the tropospheric metric, where you're not nudging, that you have a significant improvement in the ability to capture this variability over the North Atlantic. And so this begs a question, which we'll start to hopefully answer in this talk: why the Atlantic? Okay, and there are many possibilities. The Atlantic jet is very different than the Pacific jet. It has a characteristic tilt toward the north, and that is known to be associated with zonal asymmetry. So these planetary scale waves strongly shape the structure of this jet stream, both due to topography and land-ocean heating asymmetries. And these are the exact waves that I just described to you as having very deep vertical wavelengths and having the ability to directly couple the stratosphere and troposphere. So we're going to sort of pursue this line of thought as we go forward to now focus very much onto the wave coupling itself. So it's well known that the stratosphere, of course, involves the interaction of the waves and the vortex. And in particular, those vortex events that were noted by Baldwin and Dunkerton were subsequently showed to actually involve enhanced wave propagation preceding the event. So the event wasn't just spontaneously occurring in the stratosphere. Polvani and Waugh showed that there was actually an enhanced wave behavior preceding that anomalous vortex behavior. So the classic sort of metric of the wave coupling, so the sort of how the wave is behaving relative to the mean flow, is measured through something called the Elias and Palm flux. And if we're interested in the vertical coupling, then we take the vertical component of that flux, which is shown here, to be the heat flux. Okay, so the correlation of the deviation from the zonal mean of the north-south motion of the meridional wind, and the temperature here. Okay, and why is that the relevant metric? Well, if you go through the dispersion relation, and you'll find that linear theory will tell you that the vertical Elias and Palm flux is related to the vertical group velocity, and we know that the vertical group velocity is an indicator of energy, the propagation of energy, the wave energy. Okay, it's also multiplied by something called the wave activity, which in this case is proportional to the potential vorticity disturbance, and it's a quadratic function. It's also weighted by a gradient, but for the purposes of this talk, that gradient is positive. So a positive number times a variable that can change sign is an indicator of the sign of the group velocity. So we're going to use this heat flux, V prime T prime, as a measure of the planetary wave coupling. Okay, and so what does it look like, in the data? So let's look at reanalysis data. Here an interim for the entire record, 1979 to 2012. I'm showing you first just the climatology in the northern hemisphere, 20 to 90 north, surface up to 1 hectopascal. And this has been filtered by wave 1. I should have said from my last slide that wave 1 dominates this particular variable. So this is again consistent with the fact that we're dealing with planetary scales associated with surface asymmetries. So this is the climatology, and it's positive, which indicates from this linear perspective upward group velocity, upward energy propagation. But that's sort of the average representation. And if we fix our interest here on the high latitudes from 60 to 90 north at 50 hectopascal, and we can plot a distribution of behavior where the mean represents the average over this latitudinal range, but it exhibits quite a bit of variance about that mean. So here we're looking, I should have said, at January, February, and March. And so what we're interested in is in the extreme behaviors of this particular distribution. And the interpretation from linear theory, for example, on the positive side, is that we're dealing with increased upward propagation. So we're amplifying the climatology. And I'm just going to arbitrarily say that here extreme should be the 90th percentile of the mean of this distribution. And why that's an important measure is because what's even more interesting is that the distribution exhibits negative values. So these are values that are absolutely negative, and for the 10th percentile, we're talking about minus 10 Kelvin meter per second. The implication from linear theory is that this is downward pointing group velocity, or that wave energy is moving downward. Okay. So if these behaviors are very extreme, how are they coupled to the troposphere? And this is sort of very similar to how Baldwin and Dunkerton asked how are vortex extreme behaviors coupled to the troposphere. But what we would expect is that because the wave is operating on a much shorter time scale, particularly related to its vertical group velocity, then we might see more instantaneous or shorter time scale coupling. And so what I'm going to do for you now is just take a look at these take all of these days together as composites. So there's no time lag. This is all just for those days that are falling into the blue and red regions. And we're going to move into the troposphere to sort of assess how much of an impact this behavior might, what are the links between that behavior and the troposphere. So let's look at G-potential height for wave 1 at 500, and this is the climatology. So for all January, February, March days. And you can see the very characteristic mid-latitude, large amplitude wave 1 pattern. There's also some interesting high latitude structures, but it's very weak in terms of its climatological amplitude. So what I'm showing for you now on the right is just composites of those days from the distribution. So I've done nothing but just take all of those days together. And what is very dramatic about the comparison with the climatology is this amplification in the Arctic region on the order of 100 meters worth of geopotential height, where we in the climatology only have about 20. So for the negative extremes, it involves a very low geopotential heights over northern Canada and positive over Eurasia or Siberia here. And for the positive extremes, it's largely out of phase, almost 180 degrees out of phase, with the positive here over northern Canada and then negative over Eurasia. So these are very significant. Without doing any lag or any kind of low-pass filtering, we see these very large amplitude connections. And we can just overplot the connection between 500, or the phase tilt rather, between 500 and 10. So the black is the same for the negative events, and the colors are now 10 hectopascal. So when I'm going from 500 to 10, I'm going eastward with height for this particular negative extremes, which is consistent with, again, from linear theory, a downward pointing energy or group velocity. And here I'm going from 500 to 10, and I'm going westward. So that's consistent with upward. So far, this is very consistent with what we would expect from linear theory. An important issue, though, is whether wave 1 really matters in the troposphere. Of course, we know that wave 2 is very important in the troposphere, along with synoptic scale waves, as I described in the schematic. So what I've done for you is just repeat the panels, but now added to the right-hand side the geopotential height, the deviation from the climatology. So this is the anomaly. And what you can see on these days, it's very much dominated by this high latitude wave 1 pattern, which was, of course, present for the total field, which did not remove the climatology. And it's true of both the negative and positive extremes with the opposite phase. And very interestingly, you can see the node of this pattern is sort of cutting through the Pacific. And so there's not a lot of large values of the geopotential here in the Pacific, but we do see this interesting dipole in the North Atlantic, and that's going to be something that we can continue to look at. One of the implications of such a dipole would be an enhancement, in this case, of eastward winds, okay, through geostrophic balance. And so we can look at the winds at the same level and just get an assessment of how these might affect the Atlantic jet stream. So I'm showing here the climatology in black. So here's our Atlantic jet stream with its characteristic tilt toward Northern Europe and Scandinavia. And I'm overlaying on colors, actually, just the anomaly. So what this particular behavior of negative heat flux extremes is associated with is a poleward jet shift, consistent with the geopotential height anomalies. And what the positive extremes are associated with is an equatorward jet shift, so a weakening here and a strengthening here. And so while I'm not projecting onto the NAO, this is consistent with a positive NAO phase and consistent here with a negative NAO phase. And note that while there are some anomalies in the Pacific, they are very small in comparison to those in the Atlantic. So we're seeing this very clear NAO-like behavior associated with the stratospheric extremes. Another important thing is to follow the signal to the surface. So the final thing to look at is the mean sea level pressure, which again has a characteristic dipole. This is the anomaly, the deviation from the climatology. So we see the positive NAO-like phase and the negative NAO-like phase in these two composites. So what I hope I've at least convinced you of is that there is a large signal here, and it's worth unwrapping it in time. All I've looked at thus far is just the time when the behavior is extreme. And I haven't looked at the time evolution to get a sense of where the stratosphere or troposphere might be leading or lagging this signal. So that's what I'm going to show you now, is the behavior in the stratosphere for the so-called life cycle. So we're going to use that heat flux as an index, now evolving in time, but on a shorter time scale than Baldwin and Dunkerton. Here we're going to follow it at 50 hectopascal and define a period of the onset where the heat flux is positive, and then we'll transition into a phase that we'll call mature, where we reach the minimum heat flux value. So we're specifically here looking at the negative events because they haven't received a lot of attention. So the first thing to check is that the difference between the heat flux in the onset and the mature is capturing what we would expect. So for example, we look at the onset. This is what I had shown you. It looks almost identical to the climatology. And then we move into the mature phase, and what we develop is this very significant negative signal over the high latitudes. Okay, and this was what was coupled to the troposphere at 500 hectopascal. On the right, I'm showing you the phase of the wave 1 geopotential at 70 north. And you can see a characteristic westward phase tilt that you saw in the composites. And here into the mature phase, we see a weakening of this westward tilt and a slight eastward tilt, which is again consistent with the interpretation from linear theory. Another important factor to consider from the perspective of the stratosphere is how the polar vortex is behaving. So this is the problem of the waves and the mean flow. And so we can look at the evolution of the polar night jet. And in the onset phase, so this is the zonal mean, zonal wind. In the onset phase, what we find associated with these events is that there's a maximum in the mid-stratosphere. And why that's important is because above the maximum, we have this region of negative vertical zonal wind shear, which is shaded here along with regions of negative meridional wind shear. But that's an important factor because the vertical wavelength of these waves is strongly dependent on the negative value of the squared of the vertical wavelength is dependent on this negative vertical zonal wind shear. So when this is negative, what it implies is the wave is evanescent. And if the wave is evanescent, then it cannot propagate according to linear theory in this region, and so it may in fact end up overturning or leading to reflection, which would account for this downward pointing group velocity. But subsequently to this evolution, we find in mature phase that the vortex is accelerated. So the waves are transiently accelerating the vortex, so they're maintaining its strength. And this is an interesting dynamical paradigm because, as I was describing in the initial slides with the schematic, the waves tend to decelerate the vortex in the climatology, but here we're finding them accelerate the vortex transiently. This whole picture I should highlight has been noted in previous studies. Judith was a co-author and we did not ask for the index to give us this. This is what the dynamics are telling us that is consistent with these events. Another important factor is the circulation. And the circulation is important because it provides probably the most extreme behavior aside from the negative value of the heat flux. So let's look at the mature phase and look at the residual circulation. So this is our Brewer-Dobson circulation. In the climatology, it goes all the way from the tropics and descends over the Arctic. What we find for the mature phase, so when the heat flux is strongly negative, we have a reversed circulation. And this is entirely consistent with the fact that the waves are actually diverging wave activity from this region. And so the implication would be, we're basically shutting down transport from the tropics into the high latitudes. And if this behavior persists, then we would find that certainly we would have anomalously low ozone, for example. An important implication of this reversal is that air is being drawn up in high latitudes and it produces a transient cooling. So the dynamics are causing a cooling, which again is not consistent with the climatology. So this is a very different behavior than what is typically thought of for the waves, these planetary scale waves in the stratosphere. We've got a paper that's in press now on this, and we're very interested in further exploring the chemical implications and potential chemical feedbacks associated with these events. We find that they play a very important role in the very cold winters of 97 and 2011, something that is worth further exploring. So let's just now focus on the troposphere. So I've highlighted for you how dramatic the behavior can be in the stratosphere, but let's bring ourselves back to the troposphere. And here I'm just showing you what the leading order signal is in this coupling. So if we look at a Hofmahler, it's a longitude and days. at the high latitude wave 1. So wave 1 is the signal that we're interested in. It's what we had seen from those very early composites. So leading the day 0, which is masked here, but is a stratospheric precursor, let's call it, a high latitude wave 1 anomaly in the stratosphere. And what we find following that is that at 500 hectopascals, so following the stratospheric signal, we see a tropospheric signal, and it's significantly larger than what preceded it, and significantly larger in this region than the climatology. So the coupling is really, it involves this high latitude wave 1 pattern in the troposphere. And the implications of that pattern, as I described, for example, from the zonal wind perspective, if we look at latitude and time, is that that high latitude wave pattern leads to an enhancement of the winds in this sort of high latitude region that's subsequently followed by a weakening of the winds in the subtropics and mid latitudes. So the coupled behavior here would be a poleward jet shift. Okay, but that's ultimately due to this wave 1 planetary scale wave. So I just wanted to then sort of summarize, review for you what we found in terms of the reanalysis data, because it's going to be important for going forward and rationalizing our approach to looking at the CMIP-5 data. So the highlights are that planetary wave coupling is really dominant in high latitudes. There's something very, very favorable about that, about the Arctic in terms of these wave 1 or long wavelength waves. The time scale is more like a wave time scale, so we're sort of filling in the spectrum of temporal variability. And I went through in some detail the negative events because they have received so much, not as much attention in the literature, including their impact on the residual circulation. And the key was, for the troposphere, was the link to the NAO-like anomalies. And just something to throw out there, when you take a seasonal average, what we find is that the extremes are really dominating that seasonal average. So depending on how many heat flux extremes you have, that really imprints itself onto the seasonal average. I'd like just to highlight a figure from Matsuno, a schematic that he had in one of his early papers, sort of suggesting what might be going on dynamically, where at upper levels, if you have very strong winds or negative vertical zonal wind shear, you very much trap the vertical wavelength of this wave into a sort of a vertical range. And that what can happen in the mid-latitudes to trap the meridional wavelength is essentially very small potential vorticity gradients in the meridional direction. So there's a wave guide or a wave cavity here, and what you can set up is a standing wave. And so we're interested in further exploring this idea dynamically, and that's a topic of active research. But the question I want to finish up with in the second half of the talk is the role of these particular links in the CMIP-5 models, and can we use this as a new measure to say something about how the stratosphere impacts the troposphere? And why the CMIP-5 models are a useful tool for this perspective is because they include both low top, so where the stratosphere is not properly resolved, and high top models. And there's various ways of defining how you could label them as such. For example, the number of vertical levels above a certain pressure level, or a lid height, as was done by Charlton Perez. But we'll take a slightly different approach here. And so it's a very unique opportunity, as has been highlighted by the Spark-Dynvar activity. But just a food for thought is that you need both a good troposphere to have a good stratosphere, and vice versa. So I think what we're going to highlight today is just that coupling is really crucial. So the first metric that you can look at is the frequency of so-called stratospheric sudden warmings. And that was done in a paper by Charlton and Perez, and that was something that we see very clearly that distinguishes these low-top models in blue from the high-top models in red. So here he's looking at a suite of models, and on the y-axis is the frequency of sudden warmings per decade. Okay, and the shading is just the reanalysis mean and standard deviation. So in the median, the high-top models do a very good job of getting the sudden warming frequency, and the low-top models don't. Okay, but I would argue that it's only one half of the story, and it's been very difficult to understand how this behavior is impacting the troposphere. Okay, so that's still a subject of future work. So the approach that we're going to take is just follow along from that metric I presented in the reanalysis part of the talk, and just ask for each of the models how many days or what percentage of days are actually extreme from the perspective of the reanalysis. So it's a slightly complicated plot, but one way to get all of the models on the same figure is to say how many days in January, February, March do they exhibit on the y or the x-axis here positive heat flux extremes. So heat flux exceeding 40 Kelvin meter per second, which is the 10th percentile of the reanalysis in black. And then the y-axis is the negative extremes. So in this case, it's also the 10th percentile. So it's just an assessment of how extreme, what is the distribution of the heat flux in the models. And I have 29 models here. And what you can see, on average, the models, for example, if you look at the one-to-one line in the gray, they're largely falling below that line. And so they're underestimating the negative extremes. That's one thing we can take away so far. You can also begin to group the models by sort of behavior. And one reason to do this is to kind of really make the differences quite extreme. So I'm going to create a composite here of large bias models, which have very poor representations of the stratospheric heat flux distribution, and a composite of small bias models, smallest bias. This is a bias based on the stratospheric metric. And the reason I want to do this is because they exhibit very different distributions. So for the 6 smallest bias models, they accurately capture the negative extremes along with the positive extremes. This is the heat flux for the same latitude and height range that I plotted for the Erie interim. And these are dominantly high top models. The Canadian model is a medium top model, so I can't say they're all high top, but those are the 6 that came out without saying anything about where their lid should be. This is all based on their distribution. Now the largest bias clearly are significantly different, and they basically disrupt or destroy the extremes from the negative and positive side. And these are all low top. So all of these models do not have a well-resolved stratosphere. And so the next question is, does this matter for the troposphere? Is there anything systematically different between the tropospheres of these two ensembles that I've defined? So the first thing to look at is wave 1. So this is the exact same kind of color scheme where the black is the troposphere and the color are the stratosphere. And so we're looking at the smallest bias models here. And I just want to focus your attention in high latitudes where we have this maybe 20 meters worth of geopotential height that we saw in the climatology of the reanalysis, with a particular phase that is very much in agreement with the reanalysis. And the largest bias models, which have a very different phase and a very weak amplitude over the Arctic. And they also have a very weak amplitude in the stratosphere. But if we take the difference, we can see that very clearly. So where the differences are largest between these two models is in the high latitudes. And it has this characteristic phasing where the low geopotential height is over northern Canada and the high is over Siberia. So this is consistent with those negative heat flux events that I showed you as a composite, suggesting that the largest bias models are suffering from an underestimate of these negative heat flux events that are associated with downward group velocity. So you may ask, does this matter for the total wave field? So I've always, my metric is based on wave 1. So let's take a look at the wave field after subtracting the zonal mean. So this is the stationary wave field in the troposphere, which includes wave 2. You can see, for example, the low here, which is associated with the surface solution low, and the low that's associated with the Icelandic low, and this is the smallest bias model, okay? I'm not showing you analysis, so it just is what it is, and here's the largest bias ensemble, but the difference is quite striking in that, even though I've included all the wave numbers here, the difference is dominated by wave 1, and once again exhibits the phasing such that there is very low geopotential height over northern Canada and high over Siberia. So this is a very robust feature of the overall stationary wave pattern. So this is the mean. This is the mean value for the season. And you may ask, well, how does the distribution look? This not only of the heat flux, of course, but also of the behavior in the troposphere. So on the left here, I'm just showing you the distribution now for all the models ensemble average, but also comparing to the reanalysis. So by definition, my smallest bias model in blue is in very good agreement with the black. And the red model has a large disagreement with the reanalysis. So that's my stratospheric metric that I've used to define my composite or my ensemble, model ensembles. And what I'm showing for you in the bottom right now is an average in the western hemisphere in high latitudes of this eddy field. So the field I just showed you. Okay, so this half of the northern hemisphere. But now it's the distribution. So average over the whole that area and plot each day for January, February, March. And what we find is that not only are the black and blue here in agreement in the stratosphere by definition, but they're in agreement in the troposphere. Much better agreement than the red and blue. Okay, so that's one important point. So not only do we get a significant difference in the mean, which I showed you just in the previous slide, but also in the distribution. There seems to be some role of course, we know that when we change the mean, we can change the variability of synoptic scale waves in the troposphere. So that's actually pretty consistent. But the implications of this behavior can be translated into the Atlantic jet, and that was something I showed you in the composites, but here I'll really highlight for you now based on the models. So I have this ensembles of models that have a small bias from the stratospheric metric and a large bias from the stratospheric metric perspective, and here's their difference. So it's a pretty dramatic difference, but focused in the Atlantic region, and there's very small differences in the Pacific. In fact, the models have very large biases compared to Erie interim in the Pacific, but they don't share that bias in the Atlantic. So the models that have a good stratospheric heat flux tend to have a more poleward shifted jet in their climatology. This is the zonal wind, sorry. Yeah, zonal wind at 500. So the difference here is focused dominantly in the Atlantic and is basically in geostrophic balance with the geopotential height anomalies I showed you. So there was that low geopotential height, which would give you enhanced eastward winds over the North Atlantic, and the opposite sign here, okay, that would be consistent with the positive geopotential height that I had over Siberia. And these are not a small difference. This is 1 meter per second, so it's on the order of 5 meters per second, okay. But corresponds significantly, you can see, to how the the storms would be deflected over Scandinavia and Northern Europe. But I can do the exact same thing. That was the mean difference of the Atlantic jet, and now I can look at the variability of the Atlantic jet by just, again, plotting the distribution in some area. So I'm going to take an Atlantic average here, but in this region where the models exhibit a strong difference from the perspective of the eastward winds, and you can see that once again the models that are doing good in the stratospheric metric from the heat flux perspective are doing a very good job at not only the mean but also the variability of the Atlantic jet stream. So there is something very fundamental about the way that the planetary waves are represented in the stratosphere that has an imprint on the way that the troposphere, not only in its climatology, is behaving but also in its variability. I just want to give you a sense of the fact that these are not just ensembles of opportunity. One can assess that by saying, well, if we go into individual model comparisons, do we get the same result? And what I've shown you here now is taking an example from the GFDL models. So the GFDL models exhibit, one of the models occurred in the smallest biased ensemble. This is the GFDL CM3, which is a stratosphere resolving chemistry climate model. And in the middle here, I'm showing you their tropospheric model based on CM 2.1, GFDL Earth System model. Okay, and it was a part of this largest biased group of model ensembles. And so you can see very characteristic differences, particularly in high latitudes, not only the phasing but also the amplitude that are illustrated in the difference. And so once again, it's this very clear low geopotential height over northern Canada and high over Siberia. That's systematically different, even in individual model comparisons from models of the same institution. Just another highlight is the Hadley Center model, which also had this characteristic of having one model participate in the smallest bias, which is the stratosphere resolving model, and one of their models participated in the largest bias. And once again, when you take the difference of their wave 1 at 500, you see this characteristic pattern. So this is not just something that's sort of an ensemble of opportunity, I would argue. There's a systematic difference here that seems to be at play, and it's largely connected in this particular case with the metric based on the stratospheric heat flux. One of the issues I just want to address before I close is that I very carefully constructed my model ensembles. Let me just go back briefly to show you. Here were the multi-model ensembles I chose, but there was a lot of models that were outside, okay, that I didn't include, partly because they weren't necessarily lying nicely on the one-to-one line, but I'll show you physical reasons now why we might not want to include some of these models, because they are exhibiting very different behavior. And one of those models is the CCSM4, so for anyone who is interested in that, I thought I would include it here. So the CCSM4 is plotted on the left, and this is again the same color combination as before. The black is the 500 hectopascal geopotential height, and the red is the 10 hectopascal geopotential height. And the one thing I want to draw your attention to is here in the high latitudes. We have a significantly larger signal at 500, and the phasing is such that when we go from 500 to 10, there is virtually no phase tilt with height. Okay, and this is something that we've seen in previous work, but that other authors, particularly Fabrizio Sassi, who looked at the CCSM3, also saw, along with other older work by Byron Boville. And this is a symptomatic result that suggests that we have a standing wave in high latitudes. And a standing wave, just as that Matsuno schematic suggested, could result because of strong winds or negative vertical zonal wind shear, but it could also result if we have the wave encountering the model lid. That's a boundary, just as any strong wind or wind shear would be. And we see this is also occurring in other models, for example, the BCC CCSM 1-1-M. So I would argue this, looking at these models, it's good to kind of keep them separate because they're clearly doing something very different, and I would argue not physical in the context of the metric we're looking at. And so the choices that we've made are largely reflecting, the models that do a good job for hopefully the right reasons, and then the models that just don't get the effect at all. And that's where we saw the very clear differences. Okay, so I just want to summarize then, and hopefully I've given you enough background that you're convinced that the stratosphere and the troposphere are coupled, and that coupling is significant, particularly during winter. And the reason behind that coupling is due to this very deep vertical planetary scale wave and its interaction with the polar vortex. And it's well known that this interaction can lead to persistent tropospheric weather regimes. So that was established by Bolton and Dunkerton. And the phenomenology is that we associate a weak stratospheric vortex with an equatorward tropospheric jet shift, and a strong vortex with a poleward jet shift. So that was their result. Okay, it fundamentally relied on this very long time scale behavior. They also looked at what did they do? They filtered it for longer time scales. But here we've been showing now that even if we look day to day, okay, from the perspective of the wave, which of course exhibits a time scale that's much faster, and from the heat flux is then associated with upward and downward wave behavior, according to linear theory, is clearly linked from the perspective of North Atlantic to weather and climate, okay, with a particular phasing such that the node of this wave pattern is cutting right through the Pacific, and we see no significant signal there. So why is that phasing there? Well, that's largely because of the stationary waves themselves, which are what is creating the jet structure. But that is something that we're actively going to look at in some idealized models. But just to highlight then the fact that the residual circulation and its behavior during the negative extreme events was actually pretty extreme itself. So in the community have been very focused on stratospheric sudden warmings because they have this very large amplitude increase in temperature. But here I'm showing you that the negative heat flux events are just as extreme. I mean, on a day-to-day basis, they can reverse the climatological sign of the residual circulation. And that not only in the stratosphere is the behavior of significant amplitude, but also in the troposphere. And the idea being that when we have a heat flux extreme that's positive, we can associate that with an equatorward jet shift. And when we have a heat flux extreme that's negative, we can associate that with a poleward jet shift. But in the Atlantic, that's what I showed you. And the life cycle was just made clear, the sort of lead-lag relationship that we found that was clearly stratosphere leading troposphere. And it occurred over a shorter time scale than these kind of canonical vortex events. So it sort of allows us to kind of span very short times to seasonal, interannual, decadal, and longer. One of the most interesting results was that we've now, I think, found a metric that tells us something very important about how to assess the behavior of the stratosphere and when we have a good stratosphere, and what a good stratosphere from the perspective of the heat flux means for the troposphere. Okay. In particular, we found that there's a very clear imprint on the planetary wave structure and a very clear imprint on the Atlantic jet stream. Okay, and this is not something that hasn't been discussed in the literature. There's a number of seminal papers by Byron Boville who really highlighted this connection. When he changed the stratosphere, he found these large amplitude signals in the troposphere. But I think what we've been able to do with this archive is clean up that signal and make it a significantly large amplitude signal that we can detect it, and to really show us that the signal is really most important in the Atlantic. So what we found in these differences from the multimodal differences from the CMIP5 is that there's virtually no difference in the Pacific. But that doesn't mean the models are doing anything good in the Pacific. They actually have large biases with respect to the Erie interim in the Pacific, both composites, but they don't share that behavior in the Atlantic. The stratospheric models that have a good heat flux they have a very small bias compared to reanalysis in the Atlantic. I think that's progress, and I think the progress here is really hinging ourselves on a metric that has very clear links to the troposphere. An implication of the results is that, what would happen if you don't resolve the stratospheric dynamics is that you potentially are missing an amplifying effect of the NAO. And this has been highlighted in papers by Adam Scaife, who showed that if you sort of nudge the stratosphere to have a decadal signal, then the troposphere would exhibit the decadal trend of the NAO. So I think that's also very consistent. And the future work is mainly to clean up the understanding of this high latitude coupling, as I highlighted with the Matsuno schematic. Not only is there potential role for reflection, but there is a potential for resonance and instability at these latitudes, where baroclinic instability would select planetary scale wavelengths. And we're very interested in the coupling to chemistry, because it seems that there are significant feedbacks that the vortex can maintain a certain strength, whether it's weak or strong, by virtue of the wave interaction with the mean flow. But there's potentially also radiative implications through changes in ozone transport. And of course, the final important problem is an assessment of climate change. And I think it'd be very interesting to go back to look at models who have a good representation of this heat flux and go forward into the future and ask if that significantly cleans up the response to climate change, because we've have some very differing results in the literature about whether the stratosphere matters for the change in the future due to carbon dioxide. Thank you.
Thank you very much. We have time for a few questions. Yes, John?
You've been probably appropriately very careful with your phrasing of your conclusions, but I'll go ahead and take it further and say that, you seem to be on the verge of a linear theoretical explanation for the NAO in a way.
Yeah.
Not really, but maybe how far can you go? So can you quantify the variance in the NAO signal that this mechanism could explain, for example?
Right. So one thing that I haven't done in the talk is as you said, take the NAO index and really make that connection super tight. And so we're interested in doing that. One of the issues with the models is that they all have different climatology. So defining something like the NAO, which is an anomaly relative to a climatology, is a little bit of a problem. One option is just to use the same climatology. So we're actively looking at that. But I agree with you. I think what this is suggesting is the NAO might be a stationary wave. And I don't think that's not inconsistent with the literature, but it's not the dominant perspective in the literature. There's a lot of papers, Weaver and Nigam de Weaver, who have sort of highlighted this, but definitely transient eddy feedbacks have been the most persistent explanation, and it's worth pushing this, and that's an active topic that my PhD student is exploring. So hopefully we have answers soon.
Can you help me? Can you help me understand the comparison between what you're saying about the differences between the various CMIP5 models and the Gillett et al. Paper, which looked at NAM, SAM, and NAO indices. And really, I guess the fundamental point is that the variance isn't right in the past. Is that really how I should view that? Because Gillett et al. Kind of try to make the case that the models seem to do a good job on the NAM and the SAM and even the NAO. So you're saying something rather different, and I just want to understand how I should compare the two papers.
Okay. Let me just go back to Andrew Charlton's result, because I think that he is saying something that's consistent with me, and I would think that Nathan, if this is not I guess it's not the same metric, but here we're showing that from the perspective of the vortex, which is the same perspective as the NAM, that the models are very different in the stratosphere with respect to sun warmings, and that's a very robust conclusion of this paper that has appeared. One of the issues, okay, is that this is not only, I guess, this is getting at the variability as opposed to the mean. So very often we try to just look at the mean value of the vortex strength, and that doesn't seem to get us very far. It is very much in the variability, I would say, and that's partly what's being highlighted here. The interesting thing about our results is that it suggests that the variability is partly impacting the mean. When the extremes are changing, they are setting the mean value. And that's what the differences of the mean seem to imply here in the CMIP5. So it's a nonlinear, it's quite a complicated system, but yeah, I think it's largely the fact that we need to look at the variability. Just because you get the mean temperature does not mean you can tune to get that. It's harder to tune to get the variability.
Just to add to that, for example, if you look at, and that's what we definitely not try to do, if you look at an NAM index, so you remove the mean bias. In a way, you remove, and that when you look at our metrics, we specifically looked at absolute, we looked at the zonal wind, not at the anomalous structure, so to see how we really go in the extremes. Is the extremes also represented? I think that's the difference. If you just use the NAM index and then you remove part of it already, because you remove part of the bias. If you're looking at looking at the looking at the difference, and that's what we specifically use diagnostics, where you can still see it, looking at the absolute 500 hectopascal wave 1 structure or the so that's it a little bit to that.
Just wanted to ask you a question about those negative fluxes and what really determines the presence of them versus the positive situation. Is that kind of a chaotic result associated with the state of the troposphere due to non-linearity in the dynamics, or is that related to any forcing at the surface? And I'm kind of thinking, for example, that some people have been claiming that in the last 2 or 3 winters, the NAO in Europe, or the consequence of the NAO in Europe, had been affected, for example, by the change in the ice cover in the Arctic, and that could have triggered some change in the dynamics and therefore in the NAO. So is there a forcing aspect to that could then be changing as climate is changing in the future?
Right. Okay, so let me try to tackle each specific issue. The first one was just what potentially is determining the negative events. So going through the life cycle, I think we're sort of realizing that there's nothing specifically interesting about the onset period, which would be characteristic of what the troposphere is doing. The troposphere doesn't seem to be behaving in an extreme way, which is not what we see for the positive events, which have this typically related to blocking or some persistent manifestation of tropospheric dynamics. So these events just seem to be sort of average, like close to the mean, and then they become extreme. So the stratosphere itself is potentially playing a role. And one of the interesting aspects is this particular configuration of the vortex that I tried to highlight, where the maximum sits here in the mid-troposphere. And that's, of course, what causes that is another interesting question. Partly it's driven by the way the wave is interacting with the flow. Partly it could be due to some precursor. But it seems to suggest that the stratosphere is playing, there is an interaction here that's the result of the stratosphere. Now, with respect to the forcing, I don't necessarily have a good answer. We don't see any trends in this type of behavior over the historical period. Whether they may change in the future, I haven't looked yet. But I don't think it, I mean, basically because of this evolution, it's not suggestive that the troposphere is potentially playing a large role in terms of its extreme characterization. If something might happen in the stratosphere, for example, if cooling due to CO2 long-wave emission were to continue to create a stronger vortex, and you can imagine it might change it, but we haven't seen any evidence for that. So.
Hi, Tiffany. So these negative heat flux events are presumably included in the, like for instance, when Pulvani composites, the high heat flux and the low heat flux, these are sort of the ragged tail on the very end of the lowest of the heat flux events. And so these would be associated then with strong polar vortex states. But can you speak to anything? Because these sort of life cycle that you're describing seems very different from that.
Right. So in the 2D space of heat flux and vortex, which is difficult to, you don't see a strong correlation, I'll say that. But that's partly because there's a time lag, and this is sort of the manifestation of that, right? So these negative events are preferentially associated with strong vortexes because they partly are feeding back to perpetuate that state. They are strengthening the vortex. So they are, in some sense, complementary to the distribution of the vortex, but they don't map one-to-one, okay? Because this is not an anomalously strong vortex, and this maybe is becoming one, but you'd have to have multiple events like this. But there is some association, I would say. We see that interannually, that years when this flux is negative, strongly negative, the vortex is typically anomalously strong, but not all the time. So it's, yeah.
Reminiscent of the whole mass model, or very simple
yes.
models that can exhibit this type of behavior.
That's right. So there's a lot of, actually, I've been told it's, for the whole mass model, you have to do something so that the waves don't reflect. Like you have to really damp them, because they want to in that model. This is personal communication from Thomas Werner. But
I think Shigeru Yu was also exploring
yeah. So I think what we're finding is that what's being revealed here is that there is, when we look at this distribution of the heat flux, we start to see this a little bit better potentially. But as I said, the dynamical story here is not over. I think we need to look at a potential role for resonance and baroclinic instability, but it's certainly suggestive of a reflection behavior, type of behavior.